Alright, hi everybody. In this video we're going to be talking about linear programming. Specifically, we're going to be talking about the graphing details related to linear programming. And our essential question is, how are maximum and minimum values found using linear programming? So first we're going to define a bunch of terms. If I talk a little too fast for you, make sure you just go ahead and pause the video for whatever notes you might need from what we're talking about here. But here we go. First of all, what is linear programming? Linear programming is a technique that we use to identify the minimum or maximum value of some quantity. It's that straightforward, and it's got a really fancy name, but all the things that we do in linear programming are going to be things that we have already done in this course. We're just kind of putting them together into this one super useful methodology. I know that when I was in college, I had an economics course where, we spent a good 2 weeks in that economics course doing linear programming, because a lot of the people in that class were not so good at math. But hopefully you folks won't need as much time with linear programming. But let's get into it. All right, some terms that we need to know. First of all, the objective function. That's a quantity that you want to make as large or as small as possible. So in a problem-solving context, it might be something where we're trying to find, the maximum profit that we can get in a situation, or maybe the minimum cost, or some value that we want to make as large or as small as possible. Then we have constraints. The constraints are limits on the variables in the objective function, limits on what we can use. They're written as inequalities. They're usually, demonstrating that, we have some, resource that we can't exceed using that amount of that resource in our production process. And so we can write an inequality based off of that information. That will form our constraint. The feasible region. The feasible region is where all of the constraints overlap. And it gives us all the possibilities, all the different ordered pairs that meet all of the constraints of the linear programming problem. And you'll see that in a minute. So those are three very important terms that we're going to throw around here as we do linear programming problems. And you'll see us use them as we go through various examples. Next. Just a quick example here using those terminologies. We have constraints, what you see over here on the right-hand side of the screen. X is less than or equal to 10, y is less than or equal to 7, y is greater than or equal to 4, 3/4 x plus y is greater than or equal to 10. Those are all inequalities. That's what our constraints might look like. And then if we graph all those inequalities, you see x is less than 10 comes from this line right here. Y is greater than or equal to 4. Y is less than or equal to 7. 3/4 x plus y is greater than or equal to 10. And what happens is we have a region here where all the shading from all those inequalities overlap. That forms the feasible region. These are the points that are solutions to every single inequality in our system of constraints. Any point that's outside of that feasible region is going to make at least one of these inequalities false. Okay, keep plugging here. All right. If there's a maximum or a minimum value of the linear objective function, it has to happen at one or sometimes more vertices of the feasible region. So suppose I ask you, to try and find the maximum profit that you can get. The only places that you need to look are the vertices of the feasible region. So the feasible region is really important, but what really gets it for us is the vertices of that feasible region. And those are the only possible coordinates that will lead to a maximum or a minimum. The vertices of the feasible region. All right. So if you look at this, this was our example from the previous page. Everywhere where you see a vertex, boom, 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 and boom, those are the only places where we could have a maximum or a minimum. Let me go back here for a second. If I look at this, I've got these points. This is the point 4, 7 at this vertex right here. this vertex right here, I believe that's at the point 8, 4. And we've got this point over here, which is the point 10, 7. And we've got this point here, which is the point 10, 4. Those are the only places where a maximum or a minimum of our objective function can occur. All right. Let's take a look at how we do this. Here we've got a linear programming system. There are constraints. We're going to find the values of x and y that maximize and minimize p for the given objective function, which is p equals 3x plus 2y. And so one of the things we need to do is we need to first graph the constraints. So I'm going to go ahead and graph the constraints. There are all the constraints. We've got y is greater than or equal to 3/2 x plus 3, which you see with this reddish line, everything shaded above that. Y is less than or equal to negative x plus 7 is everything below this greenish shaded line. X is greater than or equal to 0 is everything to the right of the y-axis, and y is greater than or equal to 0 is everything above the y-axis. And so the overlap of all of those, and I'm going to go ahead and color it in here to make it a little bit more obvious for us, the overlap of all of those constraints is this region right here. Okay, so to find the maximum and minimum values of p, I'm going to identify all of these vertices. So we've got the point 0, 0. That's one of the vertices. We've got the point 2, 0. We've got the point 4, 3. And we've got the point 0, 7. Now what I'm going to do is I want to find which of these points maximizes and minimizes p for the objective function. So I'm going to take each of these points and substitute them into this objective function. So this is 3 times 0 plus 2 times 0, which is 0, kind of bleeding into my graph there. This is 3 times 2 plus 2 times 0, which is 6. This is 3 times 4 plus 2 times 3, which is 18. And this is 3 times 0 plus 2 times 7, which is 14. Okay, so the maximum value that we get is 18. We already found the value of p at each vertex. The maximum value is 18. And the minimum value that we get for p is 0. And that happens at the point 43. And this happens at the point 0, 0. All right, sometimes we might ask you, what's the maximum, in which case you only need to concern yourself with the maximum. What's the minimum, in which case you only need to concern yourself with the minimum. All right, let's keep rolling here. Take a look at this example. Find the maximum value of the objective function f of xy is equal to x minus y plus 1, subject to the constraints x is greater than or equal to 0, negative x plus y is greater than or equal to 0, and y is less than or equal to 2. So the first thing we do is we graph those constraints, and that gives us this region right here where all the shadings overlap. And now we identify the vertices. This is 0, 0, this is 0, 2, and this is 2, 2. And now we're going to put all of those into the function f of x comma y. F of 0, 0 is 0 minus 0 plus 1. It's equal to 1. F of 0, 2 is 0 minus 2 plus 1, which is negative 1. And f of 2, 2 is equal to 2 minus 2 plus 1, which is 1. And therefore, the max value is 1. All right. And that happens at both points, 2, 2 and 0, 0. All right, go ahead, pause the video for a few moments and try this one. Copy down the constraints and graph those constraints. Copy down the objective function and graph and then figure out the vertices and see where our maximum and minimums are. So go ahead and give it a pause, and I'll be back in about 10 seconds. All right, I'm back. So we've got the constraints that x has to be between 2 and 6. Means we've got vertical lines here and here. Sorry, I'm freehanding this. We've got y has to be between 1 and 5. Which means we've got those horizontal lines there. And we've got x plus y is less than or equal to 8. Which looks like this. And so we're looking at this region right here. And so we've got the vertices are going to be 2, 1, and 6, 1, and 2, 5, and one more. Which one am I missing? Oh, there we go, 3, 5. We're trying to find the maximum here. So we put 2, 1 into the objective function. Gives us 8. Put 6, 1 into the objective function. Gives us 20. We put 2, 5 into the objective function. Gives us 16. And we put 3, 5 into the objective function. Gives us 19. And so our maximum value for the function is 20, and it occurs at the point 6, 1. No. Wait a second. Is that 6, 2? Did I count wrong? Oh my goodness. I did. I counted wrong. Sorry about that. Whoops. Oh well. You knew what I meant. All right. Ticket out the door for you. Go ahead and get one of those tickets out the door, complete it, hand it in, and then grab a worksheet, and you've got some homework to do. All right, everybody. Have a nice weekend, and I'll see you when I'm back. Bye, everybody.